Hi everyone, let's talk about volume. This is called a volume of rotation. We're using something called the disk method. Well, the description given in our textbook goes kind of like this. We say when a region in a plane is revolved about a line, the resulting solid is called a solid of revolution, and the line about which we rotate this is called our axis of revolution. You can imagine a little disk that's formed kind of like this one below, where we take this function and we rotate it somehow about the x-axis, and we're revolving this function about the x-axis. It's called an axis of revolution. The simplest such solid is called a cylinder or disk, which is formed by revolving a rectangle about the axis adjacent to one side of the rectangle as shown below. Well, this is sort of a rectangle right here, but before we get to that, let's remind ourselves maybe a little bit about how cylinders work. If you recall, a cylinder is the kind of shape where we have a circular base, a right circular cone. Of course, we have at right angles to that base the sides. And if our base has a radius r, which I'll mark right here, radius r, and we have a height h for our cylinder, then we will recall that the volume was always equal to pi times the square of the radius, right? That's the area of the base, times the height. Okay, so we're going to use that here in this development. And the way we think about this rectangular region is shown right here. You see this purple strip right here, that we're going to call that strip width of delta x, right? So if we take that with delta x, what could we say about it? Well, if we took that with delta x and imagine rotating delta x about the x-axis, we end up with this little disk right here, right? This disk that we've found by rotating about the x-axis here in the way that you see it going around. And that volume is going to be a delta x thickness height, right, and a radius which is equal to the function height. So if we put that together right here, you will see that the volume of the disk that's formed is going to be pi times, instead of r squared, it's going to be f of x squared, right? That's our function's radius. F of x squared times delta x, which is our height, delta x. Okay, so we're going to use that, and we say, well, that gives us the volume of a delta x disk right here, but what do we do? Well, to approximate the volume under the curve, what we're going to do is that we're going to just take a bunch of these disks and add them together, kind of like you see right here, right? So if we were to go along our curve from some point A to some point B and look at the sum of all the areas of each of these disks, we're going to get an approximate volume for that. Now, I mean, that's fine if we have a fixed number of delta x disks, but what do we do? Well, remember that in the past we've said, well, let's let the number of disks increase towards infinity. That is, each one of these disks gets smaller and smaller, and so our volume approximation gets better and better as those delta x's get better. So of course, if we take that limiting value, we see something that looks an awful lot like a Riemann sum, and in fact it is, except that we're dealing with a sum of disks, and so we say, well, the volume is going to be pi times this integral from a to b of some function f of x squared dx. So that's the idea. That's what we're going to do with this. Now, in order to picture the situation, you can see that we're dealing with two different kinds of situations. One, we can deal with the x-axis as an axis of rotation. When we do that, of course, our volume is found by taking pi times the integral from a to b of f of x squared dx. And for our volume of our vertical differential, right, if we've got a function x in terms of y, we can fit a dy strip right here and rotate that about the y-axis this time, right, and get a disk of width dy and take the sum of all those. Well, there we go, right? We're going to get the pi times f of y squared dy. Same sort of idea that we were dealing with before. So the next set of examples, that's what we're going to do. We're going to take these volumes and figure it out by rotation using this method.